Good evening, professors. I am Zeho from Lab P1 Group 6, and this is our OOP assignment for Part 2. This is our presentation agenda. First, we will go through the technical implementation of our game before going into the game itself, which includes our innovative feature and the gameplay flow, and we will end off with the software design patterns that we have implemented and how our implementation aligns to solid principles. This is the overview of our implementation. It implements a layered architectural pattern which allows for clear separation between the engine and game logic. Our abstract engine layer provides the core functionality through reusable components and adopts a class-based architecture which is clearly segregated into management systems of core concerns. Our abstract classes and interfaces implemented are listed below. Our application layer contains the actual game implementation and utilizes reusable components of the engine. It contains concrete scenes, entities, and specific domain logic. We made some improvements to the engine, which includes refactoring and some new features. We improved the file structure of the engine, and it's now clearly segregated into its core concerns. We also added manager injection via the scene constructors, which reduces coupling. We moved the hitbox collision logic from the collision detector into hitbox subclasses, which aligns to OCP. We also added two scene abstract classes, one for action scenes and one for static scenes. In terms of new features, we now have animation management, which allows the generic handling of animation, and also the time life cycle management system, which allows for generic handling of time-based counting, like countdown to bomb explosions. We also added a shared music and sound effects control, which allows a consistent music and sound effects volume across all scenes for a fully customized audio experience. This is an overview of the main application components in our implementation. Game Engine acts as the main coordinator and interacts with the management systems in the abstract engine and the concrete scenes. The concrete scenes also uses management systems in the abstract engine. Gameplay scenes also interact with the domain logic sublayer, which contains game-level states and configurations, math bomber-specific systems, and round-level states. All scenes also interact with the factories for the centralized creation of concrete entities and UI elements.
Every game object inherits from the abstract entity base. Animatable entity adds animation, giving us math bomb and math player. Next, math enemy defines shared enemy behavior, giving us square enemy and circle enemy. Lastly, explosion cell and the UI elements like button and volume slider connect directly to the entity itself. The key benefits here is that shared logic is written once and polymorphism handle the rest.
On top of our engine, we built a Math Bomber game, which is a gamified learning experience to help children build a strong mathematics foundation in their younger years. Children find math boring, and traditional questions do not hold their concentration, which leads to a weaker mathematical foundation and affects the children's long-term educational journey. We aim to set them up well for the rest of their educational life by helping them build a strong mathematical foundation. Our solution is a Bomberman-like game where a user bombs enemies with numbers to answer math questions. This is an interactive game loop and allows for progressive difficulty to keep them engaged. Our innovative features build on implementations that align to OOP and solid principles. We support the extension of game modes and difficulties. One gameplay scene supports multiple game modes and difficulties. And to add more difficulty levels, we just add their configurations to the Math Bomber config class. To add more game modes, we add more configuration types to the arithmetic question generator class. This adheres to SRP as all responsibilities are segregated, and also OCP as the gameplay scene does not need to be modified to accommodate to different game modes and difficulties. Our registry-based generic entity factory enabled the type-safe creation of entities that are repeatedly spawned during gameplay like bombs and explosion cells. This enables the extension to many entity types without modifying the factory itself, which adheres to OCP. The gameplay flow starts with the start menu. The start menu allows you to choose the game difficulty, and a harder difficulty means bigger numbers and faster enemies. We also can choose input controls, which currently supports keyboard and mouse inputs. We can also choose the game mode, which has addition, multiplication, or a combination of both types of questions. We can also adjust the volume here. As the game is played, the user is spawned and multiple enemies are moving. In the gameplay scene, we can see the question, game statistics, user controls, and here we can see how the bomb and explosion looks like. To win the game, we must hit the target score. We can gain points by bombing correct enemies. And we lose the game if the player loses all the lives, and lives are lost through penalties. Here are the game rules. If the bomb hits the correct enemy, the score increases by 1 and we move to the next question. If an enemy touches a player or the player bombs itself, then the score decreases by 1, including the life count, and we move to the next question. If the life count depletes to 0, we lose the game. If the bomb hits the wrong enemy or does not hit any target, the score and life count stays the same, and the question does not change. And if the player runs out of bombs, then we move to the next question.
This screen shows the pause menu. During gameplay, the user can press escape to pause the game. From here, they can adjust the music and sound effect volume, resume the game, or quit. If they quit during gameplay, it is treated as a loss. After that, we have the end menu, which appears for both win and lose outcomes. It shows the selected difficulty, time taken, and the final score. From there, the user can either return to the main menu to start a new game, or quit the game.
I'm Jin Yang, and I'll be sharing with you the layered architectural pattern. We split our codebase into 3 layers. The engine layer holds abstract, reusable systems, which consist of collision and entity management. The application layer is a game-specific implementation, which consists of players, enemies, and user interface. And lastly, the domain sublayer, which handles game-specific rules like enemy steering. The goal here is for the engine to be reusable and never know what game is running on top of it.
For factory pattern, we implemented a registry-based generic factory to handle the repeated creation of entities like bombs and explosion cells. The entity factory interface defines a generic method T create C context, making it reusable across any entity type. The entity factory registry stores a map of entity classes to their factory functions, so when we need a new bomb or explosion cell, we just call create entity and it looks up the correct factory automatically. This avoids repetitive switch case logic and aligns with the open-close principle. Building on this, we use an abstract factory to create entire families of gameplay objects based on the selected game mode. Math Bomber Factory Producer selects the appropriate concrete factory, addition, multiplication, or mixed. Each extends base Math Bomber Factory for shared creation logic, then provides mode-specific variations. For instance, mix produces square enemies while addition and multiplication produce circle enemies. This lets us add new game modes by simply creating a new concrete factory without modifying gameplay scene code.
The command design pattern was used extensively to allow for dynamic button actions, including scene transitions, selection of configurations, and other UI trigger behavior. The main benefit of the command design pattern is scalability. It decouples UI elements from the application logic, meaning that the button object can be reused for multiple actions.
One example of implementation is the resume functionality in pause scene.
The command pop scene is stored in the command interface runnable. The client pause scene then assigns these commands to the pause button. When the pause button invoker is pressed, command runs and calls the receiver scene manager for its pop scene method. The strategy design pattern was used in the implementation of the input management system. Input source defines a strategy interface, which concrete strategies like keyboard arrow input source must implement. This family of input source implementations share the same function of converting control methods from different input sources into a shared input state. Concrete scenes are the clients choosing which concrete input source strategy to use. Input manager acts as the context and calls input source update state to update the input state, which scenes will read from to understand input intent. The strategy pattern enables dynamic input behavior, which clients can switch between different strategies at runtime.
Let's view how our projects align with solid principles. For SRP, we abstracted specific game systems like enemy steering out of the game scene and put into domain logic sub-application. Additionally, our button class really handles click events, delegating the actual actions to a runnable object. We achieve the OCP by managing entities through generic interfaces like iMovable and iCollatable. This lets us introduce new entity types without modifying our core managers. Moving to the LSP, our entity managers polymorphically cause draws on all entities. Any new entity extending the base class renders perfectly without needing any modifications. For ISP, we keep each interface small and focused on one thing, so entities are never forced to implement behavior that they don't need. And for DIP, our game scenes depends on input source abstraction rather than concrete input classes, so new control scheme can be introduced without modifying input managers.
Now let's start the game demonstration. Let's start by running the code. The start menu allows us to choose the difficulty, input controls, and also the game mode, which includes addition, multiplication, or a combination of both types of questions. We can adjust the music and sound effects volume with our mouse clicks or also arrow keys. Now let's start the game in medium mode with addition. As the game starts, the player is spawned with multiple moving enemies. The question is at the top of the screen and we must bomb the correct enemy to gain points. After we bomb the correct enemy, our score increments by 1 and we move on to the next question. As you can see, we have 3 lives for the entire game and 4 bombs per question. We also have to answer the question within the specified time. Now let's see what happens when we come into contact with the enemy. Our score and number of lives has reduced by 1. If the number of lives is reduced to 0, we will lose the game. The same thing happens when we bomb ourselves. If we run out of bombs, we will move on to the next question. We have run out of lives and have lost the game. To start a new game, we can press the back to menu button to go back to the start menu. Now let's try the game in hard difficulty with the multiplication game mode. There are more enemies and they are also moving faster now. We also require more points to win the game. As you can see, we have won the game despite the added difficulty, and the game statistics are shown in the end menu.